when the college was in the name of Delhi College of Engineering. Friends, we all are passing through incredibly difficult period of this
சொல்ல இந்த மீட்டிங்
COVID-19.
எப்படி ஸ்டார்ட் பண்றதுன்னு தெரியல சொல்ல மீட்டிங் எப்படி ஸ்டார்ட் பண்றதுன்னு தெரியல.
Hello?
Hello, Renu Verma,
Ah,
please do not, yeah.
yeah, we are all passing through incredibly difficult period of time, as you know.
நான் எப்படி பாக்குறது மத்தவங்க ஜாயின் ஸ்டார்ட் ஆயிடுச்சா
COVID-19 has created a storm in our lives,
கூகுள்
and I wish you and your families are coping well with this challenge and staying safe. Well, the topic of today's webinar is long-term bridges, past, present, and future. And let me get on with the presentation now. Bridges, as you know, are amongst the most fascinating and at the same time most challenging among all these structures. I mean, I'm a bridge engineer from the day I passed out of the college, and it is not only my profession but it is my passion too. It is a most challenging structure, and bridges, in one form or the other, has existed from very primitive times. It is hard to imagine a civilization without bridges. I mean, they are an essential part of growth and development for the human society. I just want to mention that bridges are not merely just crossing an obstacle. I mean, they connect people, they connect the communities, they reveal something about the creativity and ingenuity. I mean, they even hint at our identity. If you look at the history of bridges, and if you start, capturing the bridges.
Sir, your screen is not visible to others. I think you just.
Okay.
Your screen is not visible to others.
The screen is not visible.
This
okay.
is the message I'm getting. Just see, is it the sharing button? Yeah, just see.
Resume your presentation. Resume presenting.
Yeah, resume presenting. Yeah.
Is it visible now?
It is. Yeah, you're presenting to everyone, but yeah, now
it is visible now. Okay.
Yes,
okay.
yes.
So what I was mentioning is, bridges are amongst the most fascinating and at the same time the most, challenging, structural engineering work. And I have this is my profession as well as my passion. Bridge, as I mentioned, is not just merely a crossing. They connect people, they connect the communities, they reveal something about the creativity and ingenuity of engineering fraternity. If you see the early bridges, which is, say, around 13th century, we used to have bridges with non-metallic materials, such as wire rope, etc., vines, creepers, etc., then stone and timber. The first suspension bridge, long span bridge using cast iron chains was built way back in the 17th century, in 1620 to be precise, in Tibet. And the earliest version of the cable bridges in the modern times, which use steel ropes, appeared about 150 years ago. Bridges, are, as I mentioned, they connect the communities. What you see in this picture is basically students, school students crossing a stream by a bridge to reach to the hospital. And this is a reality in many parts of India and the world. And therefore, development is, stagnates if there is no bridge. What you see here is a smiling face of the students crossing a bridge in Rwanda. And this is a bridge which is called the Bridge to Prosperity. Very interestingly, this is a bridge which is built not by the civil engineers but by the community. I mean, it's a community participation by which they have built this bridge. And similar bridges are being built in remote areas. And they connect people, they connect communities, they sort of are very much part and parcel of our human society. Now, coming to the real, my presentation, which is which is on long span bridges, past, present, and future. This is the broad content of my presentation. I will
பாப்பா மேலாம் சொல்லு.
I will give a brief introduction followed by various types of long span bridges, along with the what is the world record on the span length. Then I will dwell upon cable supported bridges, which are the real long span bridges, and followed by conclusion. So briefly, my presentation will last for about an hour. So kindly bear with me for about an hour. So to start with the introduction, in the introduction, I will cover mainly three issues, which three important questions will be responded, and that is the brief introduction. What span length is considered as long? When we talk about long span bridges, we must understand what is meant by long span, what is medium span, and what is short span. And then what is so special about the long span bridges? Why do you need a long span bridge? Why go for long span bridge at all? Now, to answer the first question as to what span length is considered as long, there is no clear-cut definition available, but broadly, by and large, based on the type of analysis that we perform, we can say that the short span is the spans which is anywhere less than 100 meters. We would call it short span for the purpose of this particular presentation. Any span which is between 100 meter and 500 meter, we call it medium span. And long span would really mean span ranging from 500 meter onwards. Any span which is greater than 2000 meter, we will call it super long spans. Now, just for the information of all, in India, so far we have built the short span and medium spans up to 500 meters. We do not have even a single long span bridge where the span length is more than 500 meter. And in the world over, we do not have even a single super long span bridges so far built. But there are quite a few in the pipeline. I will discuss about it. So maximum span length of a bridge all over the world is about 2 kilometers, which is the higher range or upper range of long span, which is a bridge in Japan, which is called Akashi Kaikyo Bridge. And the maximum span in India is the Vidyasagar Setu, a cable stayed bridge in Kolkata, which is about 457 meter, which comes in the medium span range. What is special about long span bridges? Well, every long span bridge is unique and challenging in statics, in dynamics, and in aerodynamics. The treatment of each and every long span bridge would be different from the normal design philosophy and the normal design practice that we follow for short and medium span bridges. Such structures would require a very high level of computational skill, sound research backup with good testing facility, and we require specialist contractors also having good construction skill to do this job. Now the next question is why longer span? Well, we require long span bridges at times to reduce the number of foundation units in a difficult area where foundation construction is difficult. We would like to go for long span bridges. As an example, we can have cases where we have deep ravines or valleys, we have fast flowing rivers, we have hilly terrain where building foundations in deep gorges will be extremely difficult. Also, at times we would require in the stream long spans for providing navigational clearances and to bring about greater overall economy and convenience. As an example, if you can see, there is a hilly terrain and you can see these serpentine roads. Imagine a person who is staying in one side of the hill and he wants to go to the other side of the hill for hospital or for school or whatever. Imagine the kind of travel that he has to do, even if it is a motor road, vehicular road. It would take hours to come down deep into the gorge and then go on top. So such kind of a terrain would definitely, call for a bridge which will be bridging the two hills and which would be a long span bridge. Uh, an example of long span bridge, just to give you an example of connecting two hillocks, the slide at top shows Millau Viaduct, France, which is about 2.5 kilometer long bridge having individual span lengths 342, multiple spans of 342 meter. This is a cable stayed bridge. As far as the span length is concerned, it comes under medium as we defined, because we said anything less than 500 meter is medium. But this kind of long multiple span bridges, bridges would be covered under long span. You see, there is no very clear cut definition of what is long span and short span, as I mentioned earlier. So this is one example where have we have to connect the two difficult terrain by means of a long span bridge. Another example, if you see in the bottom right hand side, is the world highest rail bridge in India, which is under construction. This is a bridge, a railway bridge in in Jammu and Kashmir, and this bridge is spanning around 400 meter, and it is coming very soon. It is under execution now. The long span bridges are also often iconic bridges and landmark structures, as you can see. Golden Gate Bridge you see in the top right, and the Sydney Harbour Bridge. You see many of the tourists, when we forget about the civil engineers, but many common man, when we go out for tours outside India, we look for structures, and these structures are one of the sightseeing places like Golden Gate Bridge. If you go to San Francisco, you can't avoid watching this Golden Gate Bridge as a tourist. Similarly, if you go to Australia, you see these iconic bridges. We have in Delhi now a iconic bridge which is called Signature Bridge, and these are tourist attractions as well. What are the implications of using longer span? Well, there are many benefits and there are some disadvantages as well. So if we go for longer span, we reduce the foundation construction, and in some situation, this may lead to economy and feasibility. Many places, it will be impossible to do foundations in the deep gorge, and therefore you have no option but to go for long spans. There is a question of time and cost. If you go for a shorter span as compared to longer span in a situation, it may mean a huge time and cost overrun. I can quote several examples of bridges where it took more than 10 years to complete because we chose a wrong span arrangement with shorter span, thinking that it would be feasible. But finally, in the execution, we found difficulties, and there are many such case studies. It would mean reduced impact and fatigue, reduced travel time, reduced human effort, and reduced environmental pollution. All these are positives. But you see, going for long span also has some negative impacts. You increase the unit cost of superstructure. You need contractors of very high level of skill. You need the designers and the consultants of very high level of skill. The computational skills required are very high. And currently, I would say that we in India are not geared to, on our own, to sort of execute a bridge of, let's say, 1 kilometer individual span length or 1.5 kilometer. We need support from overseas to do this kind of work. Over the last 7 to 8 decades, India has made significant progress, and the world, of course, has also made significant progress in the art and science of long span bridges. I will explain in detail as we progress in the presentation as to where do we stand in India as compared to the world in terms of the span length. Now, span length records are one of the indexes for measuring our advances or technological progress in bridges achieved over the years, and therefore it is important to do this. Although span length alone is not the only yardstick for measuring progress, we have made significant progress in many field of bridge engineering, which may not be reflected truly if we simply compare the span length. Now, with this brief introduction, let me come to the second part of my presentation, which is types of long span bridges and record span length. When it comes to long span bridges, we have the following categories. One is the girder bridge, second is the arch bridge, third is extra dose bridges, fourth cable stayed bridges, suspension bridges, and hybrid bridges. Let us understand what are these stand for. If you see this slide, you see on your top left some girder bridges where you have multiple spans. It can be cantilever, it can be simply supported, or it can be continuous. These are bridges which we see every day when we in the urban areas, in crossing the bridges in river, or even in the land-based flyovers. We see these kind of structures. These are routine structures, and we call them girder bridges. What you see in the top left is it's called extra dose bridge. So you have some cable which is seen from the pylon, some cables which are supporting the deck. These are called cable supported bridges. Similarly, if you see the bottom, also you see the cable supported bridges which are called suspension bridges or cable stayed bridges. Then you have a truss system, as you see in the middle of the left side, and you have the arch bridges. These are the different forms of bridges which we have in long span category. And we can divide the bridges into three types in terms of the load sharing. One is the beam system, we call the bending system. For example, the girder bridges, they take the load by flexure, which is called bending. Then we have a form of arch bridges where the load is transferred. The principal mechanism of load transfer is compression, which is arch. And third is these cable supported bridges in the long span category, where the mode of transfer of load, principal mode of transfer is tension. Now, what is the difference? In flexure, the main load transfer mechanism is the bending. In arches, the main load transfer mechanism is compression, and in cable supported bridges it is tension. Now, what is the fundamental difference? In bending, we will see in the later part of the presentation, when we talk about bending, then the material characteristics come into play. For example, if you deal with concrete, it is weak in tension but good in compression. If you talk of steel, it is good in tension as well as compression, but if it is in compression, there is a problem of buckling. The only advantage when you transfer the load through cables where the principal mechanism of load transfer is tension, there is no problem of buckling. There is no issue of, if the cables are capable of taking tension, then you optimize the utility of the material to the maximum extent. And in fact, that is one reason why when we talk about long spans, when the spans becomes longer than 500 meter, we talk about cable supported bridges only, because all other modes of load transfer mechanism has got a limitation, whether it is by flexure or whether it is by compression. There are limitations due to instability, due to buckling, and due to the fact that the material has limited capacity in flexure. So this is an example of girder bridges. Girder bridges, you can see there are a number of examples just to show what girder. Many of you may not be aware of what girder bridges are. That's why I thought that let me briefly tell you. So you see these kind of bridges routinely in urban areas or while crossing the river. These are girder bridges where main mode of principal mode of transfer of load is through flexure bending. If you see this list, which shows what is the 10 longest span girder bridges in the world, and you can see that the maximum span in the world in girder bridge category is 330 meters. This is in China. And the top 10 has the minimum span of 263 meters. Just for information of all, in India, the maximum span that we have achieved in the girder bridge category is 170 meters. This is in Jammu, one bridge in Jammu. And so we are way behind in terms of reaching the maximum span limit. The girder material in case of the Shivanpo bridge, where the maximum span is 330 meters, is hybrid, and this is in China. One more interesting thing that you note here is out of the top 10, the 5 of these top 10 is in China. So China is dominating as far as the girder bridges are concerned in terms of the technology. So yeah. So next is the arch bridges, and in the arch bridge category, you can see various forms of arch bridges, and I think in India we have number of arch bridges, old ones. I remember in Himachal Pradesh we have done 3 arch bridges in Kulu and Manali area, Ramshila, Jia Barali, and they are off in the span ranges of about 150 meters or so. If you see the list of top 10 arch bridges in the world, then the maximum span length is 552 meters, and in the top 10 the minimum is 430 meters. Again, in terms of the arch bridges, it is dominated by China, where you can see 7 out of 10 top 10 bridges are basically in China. And material wise, if you see, the longer the span, the trend is to go towards steel truss, or the steel box, or concrete filled steel tubes. These are the 3 methodology, 3 ways by which you can increase the span, reduce the dead load, and make it work. In terms of extra dose bridges, we have, what is extra dose bridge and what is cable stayed bridge, I think we will talk a little later. But suffice it to say that extra dose bridges are also cable supported bridges, where the mode of load transfer is partly through flexure and partly through tension through cables. So it is a mixture. It is a bridging between a girder bridge and a cable stayed bridge. In a cable stayed bridge, the principal mode of transfer of load is through cables, which is tension. In extra dose bridges, it is intermediate. You can see that the girder has got a rigidity, so a part of the load gets transferred through flexure of the girder, and a part of the load is transferred through the cables by tension. India has done exceedingly well in extra dose bridges in the recent times. In last 2 years, India has, by the way, the longest span in the world, the longest bridge length of extra dose bridges in India, in Bihar, and we are matching with the world in terms of the quality, in terms of the span length, and in terms of technology as far as extra dose bridges is concerned. Till last year, up to 2018, I had the information about the number of bridges, and about 250 bridges have been 244 precisely in 2018. Now more than 250 bridges all over the world have been constructed. These extra dose form of bridges are relatively of recent origin, unlike suspension bridges, arch bridges, and the cable stayed bridges, which are in practice since about more than 2 centuries. This is the longest span extra dose bridge in the world, which is 312 meters. And this is in China, Yangtze River. This is the longest span. And you can see it's a double decker. It carries both highway as well as railway in the bottom deck and the highway on top. Then we have this category of cable stayed bridges. In the cable stayed bridge category, the longest span is in Russia, which is about a kilometer, 1100 meter to be very precise. This is called Rusky Bridge. We have done number of cable stayed bridges, and many cable stayed bridges are in the offing. But the maximum span length that we have achieved, as I mentioned earlier, is 457 meter, which is the Vidyasagar Setu. You can see in the bottom slide a picture of Vidyasagar Setu, which is so elegant. And the principal mode of load transfer, as I mentioned, is tension through the cable. You can see that the deck is so flexible and thin that it doesn't have any carrying capacity of the load. Whatever load from the live load, it gets transferred to the cable, and the cable transfers it to the pylon, and from the pylon it goes to foundation. That's the mechanism. This is a bridge. I want to spend a little time about it. This is one of the most pleasing cable supported bridge which was conceived but never constructed. This bridge was designed by T.Y. Lin to cross the middle fork of the American River at a point, which is about 10 miles upstream of the planned dam. And there was a competition, and in the design competition, T.Y. Lin won the competition for best design. The scheme was an elegant solution to a challenging topographic problem, because it was a wide, deep river which was bordered by banks with, very steep hills. To this day, the design stands as a masterwork of innovation and a masterpiece in terms of structural economy. Unfortunately, the bridge could not be constructed because the dam on the downstream side, which was supposed to be constructed, was abandoned due to environmental considerations. And since the dam was not constructed, the bridge also was not constructed. If I see the 10 longest span cable stayed bridges in the world, as I mentioned, Rusky Bridge, 1104 meter is the maximum span. And most of the bridges are in China. I mean, 5 out of these 10 are in China. And another thing is, you can see that when the span goes longer and longer, the deck is orthotropic steel. OSD means orthotropic steel deck. You see, as the span gets longer and longer, you have to reduce the dead load. And therefore, slowly and slowly, you have to convert from concrete to steel as you go longer, as you increase the span. So most of the long span bridges you will find has a steel deck. Most of the steel is optimally used in long span bridges. Coming to the suspension bridges category, we have, this is a bridge which is about 2 kilometers long in Japan, Akashi Kaikyo Bridge. And suspension bridge and cable stayed bridges are those where the spans can be, increased. Presently, we are at 1100 meters for cable stayed bridge and 2 kilometers for suspension bridges. But very soon, in another 5 years, you will see bridges having span length more than 3.5 kilometers long, which is coming up in Italy. If we see the top 10 longest span suspension bridges, you can see Akashi Kaikyo on top, 1991 meters, which is about nearly 2 kilometers. And it's a trussed bridge. Deck is of truss type. And again, here if you see China's dominance on suspension bridges. So in nutshell, when it comes to long span bridges, China has dominated, in all forms. So I think credit goes to their, very strong research units, and also their construction. They have developed very widely in in their construction technology as well. In over last about 10-20 years, this development has taken place there. Now, coming to hybrid bridges, what are hybrid bridges? Hybrid bridge is something which is a combination of cable stayed and suspension bridges. That means you have cables which are in the shape of that of a cable stayed bridge as well as the shape that of a suspension bridge. And fine example of a hybrid bridge is the Brooklyn Bridge, constructed way back in 1883 meter in New York, and it's again one of the iconic bridge which, if you visit New York as a tourist, you can't miss it. And the one which is of recent origin is the Yavuz Sultan Selim Bridge, popularly known as Third Bosphorus Bridge in Turkey, which is about 1.4 kilometer long, and it is a hybrid form. So with this brief about the various types of long span bridges, we come to the next part of our presentation, which is cable supported bridges, development and prospects in India. We discussed about, we have seen this slide earlier, and in this we have discussed about all forms of long span bridges, but now let us focus more on these three systems, which is cable supported bridges, that is cable stayed, suspension and the extra dose bridges. In fact, out of these two, let me focus only on the cable stayed bridge and the suspension bridges, because extra dose bridge also has a limitation. It can be built only up to about 300 meters. That is an extreme limit, which China has succeeded in. But otherwise, generally, it will become economical for an extra dose form only when the spans are maximum up to 250 meters or so. Beyond 250 meters, you have no option but to go for either a cable stayed bridge or a suspension bridge. Or you can go for arch bridges, steel arch bridges, which I have shown. So if you see this slide, it tells you in the long span bridge category, what is the bridge form which is most suitable. And you can see that beyond 500 meter, you only have the steel suspension bridges or steel cable stayed bridge or composite cable stayed bridge and concrete cable stayed bridge. In all other categories of type of bridges, they are suitable below 500 meters, and between 300 to 500, of course, there are many forms which are possible. If we see the evaluation of the span length for arch, suspension, cable stayed bridge, this graph tells you how we have evolved over time, and it's a very interesting graph which tells you that the form of arch bridges with masonry, we started practicing from 1810 onwards, and the span length was in the range of about 100 meters. And this is how the span length changed with time, and you can see that the oldest form is the arch form, and today we are at 500 meter, and we have not improved much in terms of span length beyond the 1930. I mean, for the last about 90 years, there is not much progress in terms of arch form. When it comes to the suspension bridges, we started in the late 19th century, and the span length, we have increased in lips and frogs. We started around at 500 meter maximum span length, and today we are at 2 kilometer. And I can tell you, if I show you this graph after 5 years, you will see that we have crossed 3,500 meters as well. So there is a huge progress we are making in terms of world over, globally, in terms of suspension bridges. Cable stayed bridges are of relatively recent origin. It started in 1950 onwards, and we can see the progress. But since 2000, for the last 20 years, we have staggered. We are at 1100 meters, Lasky Bridge, and we are yet to see a new cable stayed bridge having span length more than 1100 meters. I think this is a good graph to show how we have progressed over the years in terms of span length. If we go now specifically on the cable stayed bridges, this is how we have progressed, and I think there is not much to discuss here. This shows how we have increased the span length with time and with specific names of the various bridges. So you can see Rusky Bridge, 1104 meter, 2012 is the latest, which came at around 2006 or so. Similarly, in terms of cable stayed bridges, suspension bridges, this is how we progressed. Brooklyn Bridge was constructed in 1883, 483 meter span, but today we are at 1991 Akashic IQ, and Messina Street will be somewhere 3,600 meters, which will be way above, and when it is completed, of course. Now, what is the essential difference between the cable stayed bridge and suspension bridge? Let me give you a brief. The suspension bridge is the one where you have a long suspended cable, which is a main cable, on which the secondary cables are suspended and the deck is supported by the secondary cables. So here the primary, primary member which is taking all the loads is this prime cable, which is the suspension cable. And all these are secondary cables to support just the deck. Even if one particular cable, this secondary cable is destroyed, that may mean a local damage and not the global damage. The bridge will remain intact. In the case of a cable stayed bridge, the structural behavior is different, where the deck is supported by cables, series of cables, number of cables connected to a pylon, and then the deck is suspended by these cables. Each and every cable is a primary member. There is no secondary element here. Just to give you a sort of, just to a better understanding, if you blow up the suspension bridge at the middle, if this cable is cut, if a terrorist wants to destroy a bridge, he has to cut this one cable. That's good enough, because that would be in the failure of the bridge. But in cable stayed bridge, breaking one cable would not lead to a global failure of the bridge, because if the bridge is generally nowadays, the bridges of this form are designed for a situation where one cable can get snapped. So just breaking one cable will not mean a complete failure of the bridge. So now let us understand that in any cable supported bridge, the prime structural element is the high tensile steel wire cable. And these are the various forms of cross section of the cable, whether it is a cable stayed bridge or whether it is a suspension bridge, suspension bridge. These are the various forms in which the cable is made up of. And these are the primary element, and the entire technology revolves around how to reduce the dead weight of this primary tension element and how to maximize the unit force on this cable. And we can see now how we have progressed over the years on the cable technology. Just to give you an actual picture of the various types of cables that we use. This is called parallel wire cable, which is used in Golden Gate Bridge. We have parallel strand cables, we have steel wire ropes, we have locked coil strands. All these are, different forms which are used, and they have their own applications. I would not like to go into details of those applications in this presentation, because we will lose the focus in that case. So if you have, any one of you have visited California, San Francisco, and visited the Golden Gate Bridge, there is a museum, just on the sides, where you can see this picture of a section of this cable, which is here. And this is typically this cable comprises of. This is a parallel wire span. Main span is about 1280 meters, and this shows the cross section of the cable. How cable bridges have evolved from the primitive days? Let us understand this. You see this, primitive time, we have this, what you call living root bridges. They still exist in Meghalaya, and this is the primitive cable supported bridges where the tree roots are being used to connect. And very interestingly, these bridges still exist in Meghalaya. Another example of a Meghalaya's living root bridges. The early bridges around 13th century utilized, as I mentioned earlier, these non-metallic, material like ropes, wire ropes, vines, creepers, stones, and timbers. Why do you go for cables in terms of long span bridges? I mentioned this in the earlier. Let me explain in little greater detail. These tension structures are essentially utilized in longer spans where the other systems would not compete, as I mentioned. It may be noted here that in a flexural system, you have this stress strain curve. The capacity of the section is derived by the capacity to follow this stress strain. You have compression. If it is a simply supported structure, you will have compression at top, tension at bottom, and whether you go for reinforced concrete, pre-stressed concrete, or steel, you have to ensure that the stresses are within limits. Now, you see, in this scenario, the stresses are maximum only at the extreme fiber, and you can see that we are not utilizing the material to its full capacity, because the strain and the stresses reduces from the extreme fiber. So there is a limitation in optimum utilization when you talk about beam inflection. Now take the case of a cable. The cable is in tension, and you can see at any cross section, whenever there is a transverse load, the cable is fully stressed. All the fibers are having these same uniform stress, and therefore, if it has the capacity, it can take the it is optimally. A cable element in cable stayed bridge is as efficient in carrying the loads as any other tie. A suspended cable is almost as efficient transmitting transverse load also. I will discuss this in little detail now. Furthermore, a cable element, being a purely tension member, is more efficient than a comparable compression element such as an arch, which is encumbered with possible instabilities. With high strength steel being available for fabricating cables and use of cables for efficient transmission of loading, one cuts down the dead load, a primary design load, for longer span. This particular diagram shows how the unit weight of cable has increased or improved since we started building cable stayed bridges. In 1830, the steel that we used had a strength of 600 MPa. In 1970, we increased this strength from 600 to 1800, and today I can tell you that the research is going on to increase this from 1800 to 2200 and more. So therefore, one of the prime reason by which we can increase these span lengths beyond what we have achieved is by increasing the strength of steel strength or unit stress in the cable, because in a long span bridge, the primary load is the dead load. Live load is only a small fraction of the total load. So if we want to optimize, then we have to reduce the dead load, and one way of reducing the dead load is by increasing its strength. Now let us come to the hello. Okay. During the years, I think there is an echo I'm getting.
IAStructE admin 5 is supposed to switch off the mic.
Yeah. Okay. Thank you. So the cable stayed bridges and suspension bridges, earlier days, the design used to be based on elastic theory, and today the elastic theory is improved upon by a deflection theory. By use of deflection theory, we have ensured that we can go for longer span, we can have thin decks, and we can rely on cable stiffness. The elastic theory was, when we didn't have the computational techniques, we didn't have computers, early days, where majority of the calculations used to be done by hand. People have used the elastic theory. Understandably, you can see the old bridges. This was done in 1903, Williamsburg Bridge in New York. You can see that the truss is the depth, span by depth ratio here, whereas the modern bridges will be very thin and elegant, which is basically because of the change in the theory. These are two bridges, old bridges, which needs mention. The Niagara Falls Suspension Bridge was done in 1955, and the Brooklyn Bridge was done in 1883. Both bridges were designed by a famous engineer called J.A. Roebling. And you can see this would indicate the understanding of the designer at that time about the inherent flexibilities and possibilities of aerodynamic vulnerability of the suspension bridges. Those fears were there. So therefore, it was conservatively designed. In hindsight, one could say that the bridges, are overboard. The designer went overboard in providing the stiffness of the girders, while additionally using the cable stayed also. So a lot of margins because of uncertainties. Now, this is another bridge which is worth mentioning. This is the Tacoma Narrows Bridge in 1940, built in 1940 and collapsed in 1944. And this is where, if you compare the previous slide where we have shown you the Niagara Falls Bridge, you can see the span by depth ratio here. You can see the span by depth ratio here. And now you see the span by depth ratio here. The span by depth ratio is 350 here, which is very, very high. It was a very bold design, and it survived only for 4 months. This bridge collapsed in 1944, and I don't know whether I would like to show you a video, a small video. I don't know whether the video is there. Let me see. Okay, I think some of video is not working. Let me try again. Yeah, so let me show a video of this. Yeah, so this is a unique bridge where we could, some photographer could actually take the photograph of collapse. Very rare opportunity, and incidentally, if you have listened to the last part of this video, it says that the only casualty is the car and a dog. This photographer was traveling in the car, and the car got stopped in between when the bridge was oscillating. the gentleman came out of the car and somehow crossed the bridge when it collapsed, but he could not save his dog, which was inside the car, and the dog and the car is damaged. So you see, this particular collapse of Tacoma Bridge has enlightened all the civil engineers who designing the suspension bridges and cable supported bridges that in that period, and that led to a lot of lessons, and subsequently many of the theories on wind behavior of the long span bridges were decided on the basis of this collapse. Why did this bridge fail? It failed because of shallow plate girders supporting a narrow solid deck plate, very low torsional resistance, and failed in the flutter mode at moderate wind speed. It is mainly the understanding of the wind load which led to the collapse. A far better understanding of the bridge aerodynamics following the efforts after the dramatic Tacoma Narrow Bridge disaster was, instead of using plate girders, to use box or split box girders, use surface features for long cable stayed bridges. These are the lessons learned. Incidentally, there were many failures before the Tacoma Narrows Bridge and many failures afterwards also, but nothing was as dramatic as the Tacoma Narrows, because this was pictured. I mean, during the collapse was actually available in a video, and that has led to very good understanding of the behavior. These are some of the concerns of wind behavior. Flutter, vortex shading, and buffeting. All these things were studied later deeply, and we extended the span lengths and the, in fact, subsequent to the Tacoma Narrow Bridge collapse, many of the suspension bridges existing at that time were strengthened because of the better understanding of wind. Now, let us come to the individual, elements of the cable supported bridges and understand the behavior. The deck is the most important component of the bridge from the standpoint of aerodynamic behavior. You can see that the shape of the deck cross section can have a profound impact. The trusses, as you see on the on the top slide, this is a truss bridge and this is a box. These are the two. Modern suspension bridges are all with box because the aerodynamic behavior is far better. The earlier ones are made of trusses, and there is a significant difference in the behavior on wind. The truss attracts large drag compared to the streamlined boxes. The cross section, here you can see is that of a Messina bridge in Italy, which is under construction. You can see the drag coefficient for different shapes. Let me tell you that, when the span length is increasing, I mean, as we go for longer spans, all other loads are secondary. The wind becomes the dominating force. General conception amongst the engineers is that earthquake is a very dominating force for long spans or tall buildings. It is not so. Earthquake, it takes a second position. Wind becomes dominating, and a better understanding of wind and good, testing, wind tunnel testing becomes necessary when the span length increases. And you can see how a shape of the elements are so important while fixing the long span so that you can reduce the wind forces. So this split box is what you see here is the cross section of Messina Bridge, and this is a single box is not good from wind consideration. So it is a split box. There are 3 boxes with a transversal beam, and this is the form. I can show you another isometric view of this bridge. A schematic sketch of Messina Straits. The span length, long span is 3,666 meter main span, and you can see not only the deck has got a streamlined aerodynamic features, even the railings are having the aerodynamic features, and this is the level of detail that you have to go to if you go for a cable stayed bridge or suspension bridges of long spans. Let us come to the cables. Cables are employed in suspension bridges as main cable and hangers in cable stayed bridges stays. As I mentioned earlier, in case of a suspension bridges, this is the main cable and this is the secondary cable. And these hangers in a long span, they often experience singing due to the vibrations. And even in case of a cable stayed bridges, there are sometimes singing of the cables, very long spans, where this cable itself may be about 300, 400 meters, in length. And there are ways and means by which these vibrations can be controlled. As stays become longer, the problem of rain wind induced vibration becomes a possibility. Hangers and stays may often be provided in pairs. In such cases, wake induced across wind oscillations may also occur. So what are the various ways by which you can reduce that? You can provide auxiliary cables. You can see that how these auxiliary cables are placed to reduce the vibration. You can also use damping devices. You can see how the damping devices are placed here to reduce the damping of the cable vibration. Also, you can have possible surface features in the stay cables to reduce the rain-induced vibrations and the wind-induced vibrations. There are several ways by which it can be done, and there are a lot of research going on. And in practice, these are live examples from the bridge. You can see these dimples are placed in the cable to reduce the vibration impact. Coming to the towers, the pylons and the towers have similar problems as the of dynamic response to wind as the tall building, and the aerodynamic behavior is significant for their own safety. And you can see in a tower, in a rectangular tower, you do a wind tunnel test and you try to use many features to reduce the impact. And in one such case, the shape is changed. Instead of rectangle, the shape is changed to there are 4 cuts here, and these cuts have helped to reduce the across wind vibrations. Now, wind investigations are very common when you go for longer span bridges. Without wind investigations, you cannot, by normal statical method of wind that we do for short and medium span bridges no longer applies to long span bridges. You have to do dynamic understanding of the bridge. Its topography are very important. So you conduct wind tunnel tests. These investigations can be carried out physically by full model test or by computational fluid dynamic methods. Technology is well advanced. What you see here is a actual wind tunnel test conducted on Akashi Kaikyo Bridge, which is 1991 meter long, and you can see how the wind has deflected the model of the Akashi Kaikyo Bridge in the wind tunnel tests. And this is the kind of level of tests that you do before you finalize the wind forces. You can see another example of a Tatara bridge model, and you can see in this wind tunnel model not only the bridge but also the surrounding hillock on both sides. Everything is modeled because the topography has an important role to play in the wind behavior, and all these features are captured in the wind tunnel test. If need be, it is all required, and this is how you finalize the wind forces in designing and finalizing the suspension bridges or cable stayed bridges. Investigation through the construction stage are also very important, equally important. Other factors, far superior tools for computing to support the analytical efforts needed for these complex structures, vast improvements in cable technology, including its protection measures, great changes in construction technology. Now, India's record on cable-supported bridges. Majority of the suspension bridges built in India are for pedestrians or for light vehicles. India has capability to locally manufacture spiral strands, suspension bridges conforming to IS 9282. Facility for pre-stressing of medium-length wire ropes in the manufacturing premise so that cables with a guarantee of E value can be delivered. We have the capability. Facility for wind tunnel testing is also available simultaneously. There has been also improvement in mathematical modeling. With all these improvements, I feel it is possible now to build suspension bridges of the range up to 400, 500 meters with indigenous technology and skill, even though we do not have the cable spinning technology, which is still not introduced. Now, with this, I come to the end of my presentation. Let me conclude by saying that in this presentation, I have attempted to give you all an idea about the long span bridges, their structure types, and the span range. I tried to trace the path of development of cable bridges from the primitive times. It is seen how, based on the tremendous growth in computing techniques, material strength and quality, construction technology, magnificent and imposing bridges of great aesthetic appeal can be built. It is clear that the Indian industry is not yet technologically geared to fully exploit the benefits of long span bridges. Complete elimination of this long span family of bridges surely signifies loss of technological parity with the world. Considering the large-scale infrastructure development that is taking place in India, it is high time that industry recognizes the need for building such long-span bridges for sustainable growth. Thank you very much for patient hearing. Thank you. Hello. Hello.
Yes, sir.
Thank you, sir,
Yes,
for your
sir.
lecture. I request from the audience if there are certain questions. Hello. So now, sir, can we take some few
Sure, sure.
questions? Yeah, if anybody wants to ask something, so you can please unmute your mic, and one by one we can have the queries from Alok, sir.
Hello. Hello. Am I
Yes,
audible?
yes.
Sir, good afternoon. My name is Prashant.
Yeah.
I wanted to ask that if in a place at the bridge site where there is no technical problem in constructing in
Yeah,
foundation,
please.
so what should be economical? Either to create a new foundation or to increase the span?
You see, you have to do a techno-economic feasibility study. Normal way of deciding the structural scheme and the type of bridge is by carrying out a techno-economic feasibility study where you work out on various options, and do a analysis considering the cost, time, construction technology, everything, and then take the decision.
Okay. So that should be based on feasibility report, sir.
Yeah, yeah. You have to first perform a feasibility study where you do option study of various possible options, and then choose the best one. Decision metrics may consider sustainability, economy, time of construction. So there are many parameters which needs to be considered for taking the decision.
Great. Thank you, sir. Thanks for the presentation.
Thank you. Hello.
Anybody else would like to ask the question?
Good afternoon, sir.
Yeah, good afternoon.
Am I audible, sir?
Yes, yes, very much.
Sir, sir, you told that the gutter span we have the 300 meters. We can make the gutter span, but in India we can only make 190 meters. Why are we lacking in this? What is the reason behind this, sir?
Yeah, that's a good question. Yeah. No, we are not lacking at all. What is happening is, beyond 170 meter, which we have done, any other form of girder bridge works out to be uneconomical as compared to extra dose bridge or cable stayed bridge. So it's not that we have not built bridges more than 170 meter, but the girder form of bridge is not economical, as compared to other forms like truss bridges, like arch bridges, they come out to be more economical. That's why we have not done.
Thank you, sir.
Any other question from the audience?
Good afternoon, sir.
Yeah, good afternoon.
Sir, what can be the maximum deflection in long span bridges? Is there any guideline for maximum deflection in bridges?
Yeah, good question. Yeah, I mean, there are guidelines, but the deflections, for example, this Akashik IKO bridge, 1991 meter, the deflections is as high as 1.5 meters or so. So, but then in a span of 2 kilometers, 1.5 meter is not a very large deflection. And secondly, you see, I mean, good that you raised this point, because that enables me to clarify that, you see, the suspension form of bridge has larger deflection as compared to the cable stayed form of bridges, and the extra those bridges will have lesser deflection. So therefore, that is one reason why you will find that railways, there are very few railway bridges with long span, because railways would require a relatively lesser deflection for running their the rolling stock and etc. So therefore, when it comes to long span bridges, if you make it flexible, that means suspension bridge is a flexible form, then highway bridges is okay, but for railways you have to increase the rigidity of the bridge by some form. So hybrid form may be a better if you have to pass the railway.
Sir, but how we can classify that after this much of deflection, this bridge needs health monitoring, or this is in danger?
No, that is, for long span bridges, there are some international guidelines and codes. There are American PTI guidelines, there are FIB guidelines, FHWA guidelines. They are available. The guidelines are available. Since we are not into the long span in India, Indian guidelines are not there. But if you go to the international, see the international codes, there are guidelines available for acceptable deflections depending upon, what is the function of the bridge.
Thank you, sir.
Any other question? So if we do not have other questions, so I would like to thank Alok Bhowmick sir for taking out, sharing his knowledge about a vast knowledge that he has, but he could share it, he had time and he shared it for the long span bridges. Thank you, sir, for sharing your knowledge and your views. And I also thank all the participants for their patient hearing and a successful conduction of the first event by the Indian Association of Structural Engineers Student Chapter at DTU. Alok Bhowmick sir has, promised me that he'll take the first lecture, and he has fulfilled it today. Though we were planning it after Holi to have a one-to-one interaction, but anyways, this was a very informative, very nice lecture. Thank you, Alok Bhowmick sir, on behalf of Delhi Technological University.
Thank you very much, Dr. Shilpa. Thank you.
And
thank you very much.
I also thank my student coordinators, Salil, Devashish, Ishant, and Avinash. So we've started with the activities of the association, and also Harsh of second year student. And I request all the participants that you can please share the topics on which you would like to have the webinars on structural engineering topics, so that the student chapter of Indian Association of Structural Engineering at DTU can take a lead in organizing such webinars, and also after the university reopens, we can have one-to-one interaction. Thank you, one and all. We'll be sharing we will also
Dr. Shilpa,
share. Yes, sir.
Dr. Shilpa, I would like to, I would like you to convey a message to all the students, let us encourage them to ask more questions. They can email to me through you. They can email. You can compile all the questions, and it will be my pleasure to answer. If those who could not ask questions today, they
Yeah.
feel free to sort of put it in a mail.
Yeah. So I request all of you that you can you can post your questions on the WhatsApp group that we have found, and then I can compile it and send it to Alok Bhowmick sir. And all the answers I'll be sharing it on the WhatsApp. And also, please, the Indian Association of Structural Engineers, some of you must be the members, the student members of this organization. So we invite you on behalf of Indian Association of Structural Engineers to become the student members of this association. And I, being the faculty coordinator of this at DTU, you can take the forms from me, fill it up, and it's on an amount of rupees 118. The registration fees is 118 is the GST. So all those who are interested to become the student members are most welcome to do so. And kindly post me the topics on which you would like to have the webinars. So at this outset, I would like to thank one and all for a very good participation and making this webinar a success. Thank you one and all. Thank you, Alok Bhowmick sir.
Thank you, thank you, thank you, thank you.
Thank you, sir. Thank you one and all. So we'll be sharing the presentation after